The wet bulb temperature is the temperature read by a thermometer covered in a water-soaked cloth over which air is passed. The dew point temperature is the temperature to which air must be cooled to become saturated with water vapor. These definitions come from Wikipedia, and likely if you're here, you've already read them. What you're missing is the difference between these two temperatures. Because let's be honest, they kind of sound like the same thing. Today we're going to get a feeling for where they lie relative to each other. A thing to note before we start is that both of these definitions talk about air. Wet bulb temperatures are predominantly used when talking about the air-water system, but dew point temperatures can be used for any gas that contains some sort of substance that is about to condense. I've already made a video talking about wet bulb temperature. This video spoke about the relevance of wet bulb temperature measurements in process engineering. I'm going to assume that you've watched it so that we're able to differentiate between wet bulb and dew point for this video. The wet bulb temperature of a gas and the dew point temperature of the gas are not the same temperature. I think it's best to illustrate this graphically. To show this difference between wet bulb and dew point, we're going to look at humid air. This is a psychrometric chart from Wikipedia. It tells us various things about air that contains water. There's a lot going on here, so let's go through it one bit at a time. On the x-axis, we have dry bulb temperature. This is simply regular temperature the way you have always understood it. Nothing special here. On the y-axis, we have absolute humidity. That is, how many grams of water does each kilogram of dry air contain? Totally dry air lies along this line, the x-axis of 0 grams water per kilogram of dry air. You can see that the vertical temperature lines are different lengths, and that's because air can only hold so much water. The warmer the air, the more water it can hold. As an example, at 20 degrees Celsius, a kilogram of air can hold about 15 grams of water. At 30 degrees, this capacity goes up to around 27 grams of water per kilogram of air. We can draw a line through all of these maximum water contents for each temperature, and we get the line of 100% relative humidity. This is also known as the saturation curve. If we take each vertical portion and divide it up equally, we can get various curves showing different percentages for various relative humidities. So air that has a relative humidity of 50% at 20 degrees has about 7.5 grams of water per kilogram of dry air, while the same 50% humidity at 30 degrees represents a water content of about 13.5 grams of water per kilogram of air. Already here we can start seeing what we mean by dew point temperature. Take air at 30 degrees and 50% humidity. We said that the dew point is the point at which the first droplet of liquid forms when we cool a gas down. As long as we are below the saturation curve, there will be no liquid, so we need to get above the curve to start forming liquid droplets. If we cool down the gas by dropping its temperature, we move from right to left. When I cool it down, I am not changing the water content of the gas before I formed a liquid droplet. The water isn't going anywhere until I get to the saturation curve, so I stay at a constant absolute humidity. However, as I cool down, the relative humidity is going up. The point at which I hit the saturation curve is the first point at which the gas is fully saturated at 100% relative humidity, and that means water will start to condense. This is the dew point temperature of the air. So the dew point of air at 30 degrees and 50% relative humidity is about 18 degrees. What about the wet bulb temperature? Well, we already have lines of constant wet bulb temperature drawn on this chart, but we need to understand what they are showing us. Remember we said that when air is saturated with water, then there is zero difference between wet bulb and dry bulb. You should be able to see that on the saturation curves. The wet bulb temperatures are the same as the dry bulb here. So why do the lines of constant wet bulb temperature slope at this angle? The answer to this can be found if we overlay the lines of constant enthalpy. Enthalpy is simply the energy content of this air-water system. Can you see that these lines are perfectly parallel to the wet bulb temperature lines? Let's take a moment to understand why this is the case. Let's go back to our 30 degrees, 50% relative humidity point. Imagine we use this air to measure wet bulb temperature. Remember, we wrap a wet cloth, technically it's called a wick, around the thermometer bulb and get the water to start evaporating. The evaporation of the water removes heat from the air to cool it down, so the temperature drops. But at the same time, the water content of the gas increases because the water is coming into the air. So why do we say that the energy content of the air is the same? Let's consider what happens when we're doing this wet bulb temperature measurement. Let's define our system as the air around the thermometer bulb around a wet wick. To start off, the air has some temperature and some amount of water. The air cools down when we measure the wet bulb temperature. Its temperature is dropping because it is losing energy. Where does that energy go? It goes into evaporating the water contained by the wick. The heat of vaporization of water is removing energy from the air. This is the same thing you feel when you step out of the shower and you feel cold due to the evaporation of the water from your skin. So the water has absorbed the energy and is now in the vapor phase of the air. This means that the water content of the air has increased. But can you see the water molecules that took the energy away from our system initially have now entered that system? It is for that reason that we say the enthalpy of our system has remained constant. The temperature of our system has dropped because energy left the system to vaporize the water. But now that vaporized water is a part of our system, so the enthalpy has not changed. It is for that reason that a line of constant wet bulb temperature lies on a line of constant enthalpy. So for dew point, we ran horizontally across until we hit the saturation curve to get the dew point temperature. For wet bulb temperature, we run along a line of constant enthalpy until we hit the saturation curve. So air at 30 degrees and 50% relative humidity has a wet bulb temperature of 22 degrees, and that is obviously different from its dew point. We could use any starting point, and the procedure to read off dew point and wet bulb temperature would be the same. Maintain a constant water content until you hit saturation to get dew point. Maintain a constant enthalpy until saturation to get wet bulb. I chose the psychrometric chart because this is the most common application of wet bulb temperature, so it's a useful tool for showing this difference graphically. In reality, you aren't going to find charts like this for all the combinations of chemicals you get. You can, however, perform thermodynamic calculations to get the wet bulb temperature and the dew point temperature of any combination of gases. Hopefully, this graphical method helps you differentiate a little bit better conceptually.